Hey everyone, and welcome. Think about it for a second. From a bird flying overhead to the planet we're all standing on, pretty much everything is in motion. But how do we actually describe all that movement with any kind of precision? Well, today, we're going to break down the fundamental science of how things move, piece by piece. Alright, so here's our game plan. First, we're going to start with the kind of surprising idea that all motion really depends on your point of view. Then, we'll build up our physics toolkit with concepts like distance, speed, and acceleration. And finally, we'll put it all together with some powerful graphs and equations. Okay, first up, we've got a pretty mind-bending idea, but it's absolutely crucial to everything else we're going to talk about. Motion isn't absolute. Nope, whether something is moving or just standing still depends entirely on who's doing the watching. Let's use a classic example to make sense of this. Imagine you're on a moving bus. To you, the person sitting next to you is perfectly still, right? But to someone on this sidewalk, both of you are zooming past. You see the trees flying backward, but the person on the street sees the trees as stationary. And here's the wild part. Both of you are completely correct. So to stop all this confusion before it starts, physicists need to agree on a common starting line. We call this a reference point, or sometimes the origin. Without agreeing on one, trying to describe motion is pretty much meaningless. Let's move on and add a couple more tools to our kit. Now that we have a starting point, we got to talk about the journey itself. And as it turns out, there are two very different ways to measure it.
This slide lays it out perfectly. On one side, you have distance. That's the total ground you covered. Just think of it as what your car's odometer reads. Simple enough. But on the other side, you have displacement. That's just the shortest straight line path from where you started to where you ended up.
To really see what I mean, just imagine this. A car starts at point O. It drives 60 kilometers out to a point we'll call A, and then it turns right around and drives 35 kilometers back, ending up at a spot called C.
So, let's crunch the numbers. The total distance that car traveled is 60 kilometers out plus 35 kilometers back. That's 95 kilometers. A pretty long trip. But what about its displacement? Well, it only ended up 25 kilometers away from where it started. See the difference? It's huge.
Okay, so now we know how to describe where something is and how far it's gone. The next logical question is, well, how fast is it doing all that? And this brings us to three related but very distinct ideas: speed, velocity, and acceleration.
Now, this is something people mix up all the time. But in physics, you gotta be super precise. Speed is just a number. It's how fast you're going. But velocity adds a crucial piece of information: direction. So 100 kilometers an hour is a speed. 100 kilometers an hour north, that's a velocity. And Usha's swim in the pool here is the perfect example to clarify this. She swims a full lap, that's 180 meters, in just 60 seconds. So her average speed is a pretty quick 3 meters per second. But because she ends up exactly where she started, her total displacement is 0. And if your displacement is 0, your average velocity is also 0.
So what do we call it when an object's velocity isn't constant? Well, anytime you change your velocity, and that means speeding up, slowing down, or even just making a turn, we call that acceleration. It's definitely not just about stepping on the gas pedal.
Let's check out Rahul on his bike. In the first case, he starts from a complete standstill and pedals up to 6 meters per second over 30 seconds. Then, in the second case, he hits the brakes, and his velocity drops by 2 meters per second in just 5 seconds. And this graph shows exactly what's happening. In that first bar, as he's speeding up, his acceleration is positive. But look at the second bar. When he hits the brakes, he gets negative acceleration. We often call it deceleration. His velocity is changing in the opposite direction of his motion. You know, looking at a table of numbers is fine, but sometimes a picture tells a much better story. And physicists absolutely love using graphs to visualize an object's journey through time. So let's start with a distance time graph. If an object's moving at a nice steady speed, you're going to see a perfectly straight slope line. But the moment you see that line start to curve, boom, you know its speed is changing. It's accelerating. Now what about velocity time graphs? Here, a flat horizontal line means your velocity is constant. A straight sloped line means your acceleration is constant. But here's the really cool part. The area under that line actually tells you the total distance the object traveled. It's like a secret hidden in plain sight. Okay, so we've got our definitions down and we know how to visualize motion. Now it's time to assemble all these concepts into the real power tools of physics, the equations. And we'll finish up with a fascinating little paradox of motion.
For any object that's moving with a constant acceleration, these three equations are your absolute best friend. Seriously, think of them as a physicist's crystal ball. They connect an object's initial velocity, u, its final velocity, v, its acceleration, a, the time, t, and its displacement, s. With just a couple of these pieces of information, you can predict the future of that object's motion. It's incredibly powerful.
But wait a minute, this leads us to a really tricky question. We said acceleration is a change in velocity, and we said velocity is speed and direction. So is it possible to be accelerating if your speedometer isn't changing at all?
Believe it or not, the answer is a huge, definite yes. And the simple image of a stone being whirled around on a string holds the key to understanding how.
So here's the deal. Even if that stone is moving at a perfectly constant speed, its direction of motion is changing at every single instant. And since velocity includes direction, that means its velocity is constantly changing. And what did we say a change in velocity is? That's right, it's acceleration.
This quote right here just nails it. The change in velocity can come from a change in its magnitude, that's the speed, or from a change in its direction, or both. This one idea is the key to understanding so much, from satellites orbiting the Earth to just you in your car making a turn.
So there you have it. We've gone from the relativity of a moving bus to the constant acceleration of a spinning planet. Motion is a deep and fascinating story. So my final question for you is, now that you know what you're looking for, where else in your daily life do you experience acceleration without ever changing your speed? Think about it. Thanks for watching.